Okay, so first we need to find a way to approximate our objective function around the known point. So in order to tie that into our specific application, so let's say we are trying to solve a reinforcement learning problem, and we have a specific policy. And I would say that the objective function, the one that we're trying to solve, is the J, right? The expected sum of discounted returns for some policy that is defined by some tunable parameters. And we don't know the values of that J for different policies, but we do know it for our current policy, right? We have a policy, we run it in the environment, and we can observe some samples of the expected sum of returns, right? We sample the environment. But this is mainly for the current policy. And we would like to somehow approximate the function, the general J function, also for other policies that might be far away from the policy that we are currently looking at. So there is a very specific, again, mathematical tool for approximating a general function, a function, around a known point, which is known as, so Vabav, this should be an easy answer.
Taylor series.
Yeah, good job. Yeah, this is. We can use Taylor series of approximation, and indeed we will use them during this lecture. So just as a reminder, you should have covered that in your undergraduate degree, but I'll just give you a quick reminder. In Taylor series, we're trying to approximate an unknown point, fx prime, around a known point x. Okay, so we're trying to evaluate the function at location x prime around a known point, a known f of x, right? We know f of x, we know the value at x. We know more than that, actually. We need to know not only f of x, but we need to know f prime of x and f double prime of x and so on. We also need to know the derivative at that point. Or that's what is assumed when using a Taylor series. So indeed, we assume to know the derivative, the first derivative at the known location, at location x, the second derivative, the third derivative, and so on. By the way, if we know all of the derivative until n goes to infinity, then hopefully you can intuitively see how we'll have all of the information. We'll be able to redefine the entire function, and then we'll have all of the information to actually approximate any point as far as arbitrarily far from point x. The problem is usually that we don't know all of these derivatives. We might be able to compute the first derivative, second derivative. Actually, there's a bigger problem here. It's not only that problem. The bigger problem, and we'll see it in a second, is that once we go to higher and higher order of derivatives, it's not a problem if we have a 1D function, right? A function that is only dependent on x. But as we have a higher and higher dimensionality of functions, what will happen to the higher orders of derivatives? You know? So what would be the first order derivative? All of the partial derivatives, right? This would be a vector, also known as the gradient. But the second order derivative is already a matrix. Which matrix?
Asian matrix?
Asian matrix, yeah. Okay, and it grows exponentially with the dimensionality, right? And so that will be our main point. But once you know all of these partial derivatives, then you can find the function's value at an unknown location, as long as you know all of the partial derivative at the known location, at the location x, and obviously you know the distance between the point that you're trying to evaluate and the known point. What's important to notice is, first of all, the more higher derivative that we assume, the more accurate our approximation gets. You can see it here. Okay, so you can see what will happen only in a first order. A zero order derivative is just a straight line, right? No, sorry. The first order derivative is just a straight line, And that will be your approximation, and you can see that it's very bad as you go further away. If you add the second order derivative component to your approximation, you can see that your approximation becomes more accurate, but again, locally. And the more, if you add another order derivative, it becomes even more accurate. So you can see that the higher order of derivative that we consider, the better it is for our approximation. And also you can see that for a given approximation, level of approximation, it's always more accurate. Usually it's more accurate surrounding the known point, right? If you move the known point, your trusted region, the region that you approximate the function well, also moves with that. It usually surrounds, it's dependent on the distance of the approximated point from the known point. And that's important in order to motivate the trust region method. Finally, one more background method or background tool that I would like to discuss is Newton's method. And we are also going to use this in the algorithms that we are covering today. So when we consider the main issue here, as we've seen before, is that when considering high-dimensional optimization problems, the k-order partial derivatives is size n to the power of k. It grows exponentially, right? Initially it's just a gradient, then the Haitian matrix, and it explodes. It grows with the dimensionality, with the order of the derivative. So what we usually do is we limit the order of derivatives that we're considering. And a common way to do it is to limit by the second order Taylor approximation. Right? If we use just a second order Taylor approximation, we'll need to compute the gradient at the known location, let's say a known location C. We'll need to compute the gradient of our function at the known location, and we'll also need to compute the Haitian of the function, of the objective function in the known location. Right? Once we define those, we see that we can define the delta, or the change from our known point C, or we can define the difference between the known point C and the optimal point X, and that will give us the step size towards the optimal point, right? It's X minus C, if we consider X to be the optimal point. And we can actually find that step size towards the optimal point by setting the gradient of our objective function to 0, but the gradient with respect to the step size. So we're going to find the optimal step size. And you can indeed take the derivative of this function with respect to X minus C, and it's down here, and make it equal to 0, and then you can compute you just move X minus C around, and you get the Newton step direction, X minus C. That is, it will tell you how to move from C, your current location, towards the approximated optimum X. It's an approximated optimum because it uses a second order Taylor approximation, right? So it's not the real function that you want to optimize, but hopefully a good enough approximation. Now we're going to add some, so later on we're going to use this type of step size, and we'll see it later on. Next we're going to add some trust regions.